Okay, while we're waiting for the slide to work. The next section is the field characterization study of synthetic turf fields. Presenter is Ms. Rebecca Peloso from OEHHA, and then followed by the team of the Lawrence Berkeley National Lab, Dr. Randy Madalena, Dr. Woody Daup, Dr. Hugo Distaliet, and Ms. Marian Russell. So we'll start with Rebecca Peloso.
Good morning. Thank you. Today I will be presenting regarding the field selection and sample collection with the synthetic turf study. So here we have a timeline of the study. Today is May 25th, 2018. And our phase 1 began in January of 2016, and it involved the protocol development for chemical analysis as well as sample collection. Additionally, during this period, initial crumb rubber samples were collected and used for further protocol development. In phase 2, which took place in early 2017, we tested and finalized a sampling protocol. Our focus today will be on phase 3, field sampling. This took place throughout 2017 and involved field sampling to characterize field conditions in California. In the next section, Dr. Madalena will present some preliminary data for the sample analysis. This is a map of the target number of fields that we set out to sample in California. We use a random stratified method to select fields, as discussed in the last panel meeting. Ultimately, we stratified by 2 main factors. The first is climate zones and regions. And as you can see in this map of California, we have grouped 5 different climate regions according to the climate zones. We also stratified by age of field, categorizing fields as old or new. Our target number of fields were 5 new and 5 old fields for regions 1, 2, and 3, and a target of 5 fields total for the combined regions of 4 and 5. And as a reminder, we combined regions 4 and 5 because they have fewer fields located in these regions. Our total target was to sample 35 fields throughout California. Our stratified random sampling protocol also involved randomly sorting fields in each region and contacting fields by order of the random list until our quota was met. Our field study goal was to collect samples to quantify chemicals that may be released from synthetic turf fields. Samples of infield crumb rubber and environmental matrices were collected from 35 synthetic turf fields across California. Here we have a picture of Dr. Madalena, along with the equipment used for sampling. And this next photo is a typical setup of the equipment on the field. And as you can see, we have a soccer goal, net, some activity on the field, and samplers set up around the goal to collect environmental data, of which Dr. Madalena will be discussing more in detail in the next section. And we also collected infill crumb rubber in 7 to 10 pre-selected locations throughout the field. The following tables will show the actual number of fields sampled in each subgroup. Region 1 shown here covers the southern coastal areas. We sampled a total of 8 new fields and 3 old fields in this region. New fields were categorized as 0 to 9 years old, to less than 9 years old, and old fields were categorized as age 9 or above. We did not sample any fields from the unknown age category. We sampled 2 fields that contain a cork and crumb rubber mix infill. So the total number of fields sampled in region 1 was 13, or 3.5% of all fields in region 1. As you may notice, we oversampled fields in this region. Part of this reason is due to a discrepancy with the field age reporting. For example, we were assured a field was a certain age, and post-sampling, it was brought to our attention that fields were newer than originally thought. And due to this discrepancy, we moved some fields from the old age group to the new age group after sampling. And during recruitment, sometimes we did not get responses or came to find out that fields were removed or replaced. And this is how we came to know of the cork and crumb rubber mix fields. So these fields were listed as older fields in our database, and upon contact, we were told that they were recently replaced with this new infill type. We decided to sample these fields as we began to hear more about cork and crumb rubber as an infill option. Region 2, shown here, covers the northern and central coast areas. We sampled a total of 4 new fields and 5 old fields in this region. We did not sample any fields from the unknown age category. The total number of fields sampled in Region 2 was 9, or 3.3% of all fields in Region 2. As you can see, we were unable to recruit 1 additional new field, but we were very close to our goal of 10 fields in this region. Region 3, shown here, covers the southern interior valleys and northern central valley. We sampled a total of 5 new fields and 6 old fields in this region. We did not sample any fields from the unknown age group. The total number of fields sampled in Region 3 was 11, or 4.7% of all the fields in Region 3. Again, we oversampled in the old field category by 1 field. Here we see the combined Region 4 and 5, which covers the southern high and low deserts and mountainous areas of California. We sampled 1 new and 1 old field in this region. We did not sample any fields from the unknown age category. We reached out to field owners of all the fields in this region and only received 2 agreements to sample 2 fields. Therefore, our total sampled are 2 fields in Region 4 and 5. This seems like a small number, but I would like to point out that there were so few fields in this region compared to other regions. And our final sampling percentage was actually higher than all the other regions at 8.3%. Here's a map of California summarizing the number of fields sampled per region. Overall, OEHHA with the Lawrence Berkeley National Laboratory sampled 35 fields. 33 were crumb rubber infill fields, and 2 were new synthetic turf fields containing cork and crumb rubber mixed infill. And here are the figures showing the age distribution of the fields. In Figure A, the blue represents the cumulative distribution of field age in California according to our field database. After sampling all 35 fields, we plotted their cumulative age distribution in orange. Coincidentally, the age distribution of sampled fields follows a similar trend to the age distribution of fields in our database. I would like to point out that it is possible that the blue curve representing the overall field age distribution may be shifted due to some fields being mislabeled as older in our database. Figure B shows the age distribution among the fields sampled. The age distribution of the new field group is spread out. We did not sample fields less than 1 year old. In the old fields group, most of the fields sampled were between 9 and 11 years old. This is likely because, according to field owners that we interviewed, replacement of fields tend to begin when the field is approximately 10 years old. By age 14, most of the fields have been replaced. This may be one of the reasons why there are relatively few fields 14 years or older in the old fields group that we sampled. I'd like to thank you for your time, and I would like to introduce our next presenter, Dr. Madalena from the Lawrence Berkeley National Laboratory.
Okay, I'm on now. Thank you again for coming out and spending your time with us. Give us a chance to catch up on what we've done. The first presentation, I think, was very effective at talking about what we wanted to do. And now I'm going to, next few minutes or 15 minutes or so, try and tell you what we did do, what we did see, what we did find, which is always, you know, what you try and do and what you do get done is sometimes slightly different, but at least we know what we did. So I want to share that over the next few minutes.
Could I interrupt you just for a moment?
Yep.
Dr. Sheldon, can we ask questions at this point? Well, it depends on their answer, I guess. Okay.
Yeah? Okay, just make sure you don't forget that question. So I did change the title from the agenda slightly. It's more of an overview of environmental and physical conditions in this talk, and then I'll hand off to the rest of the day will be spent talking about preliminary results, things we actually found. But right now I want to give a good sense of what we saw out there when we were collecting measurements to give you a feel for what the measurements might represent. Like I said, the previous presentation did a nice job telling how we stratified on the age and recruited and selected. And I'm going to show how that distribution plays out towards the sampling schedule, what months and temperatures and such we sampled in, show you a little bit of typical on-field conditions and how all of the things we measured interact. Then we're going to step back and start looking at the distribution of conditions that we found on the field, wind speed, temperature, solar radiation, things like that that might affect the outcome. When we have samples, we'll come back with numbers that we'll know where those numbers came from. And then we'll finish with the distribution of sort of the human input to the problem. The last meeting we talked about bringing humans into the equation, having them conducting activities in the field while we're doing measurements and try and make them more representative. So I'll finish with that. Starting with the distribution of monitoring events, we started, the two first bars on the top are from our pilot study, so prior to the last meeting that we had. And then we jumped out and started doing the study in the field. And the monitoring events are shown on the axis up to, in October, we had the most sampling events, 8. So that's how you read the chart. There were 1 in February, 1 in April. Scheduling was, as Rebecca indicated, dictated by response from the field owners, but also dictated to a certain degree by weather conditions. We didn't want to work in the rain because we had a lot of expensive equipment out there. Travel logistics, trying to get from point A to point B in a hurry, and getting things to the field for us to collect measurements. The sampling media had to be sent back to the lab, processed, reloaded, and sent back to us in the field. And we only had so fast that we could turn that around. So some of that kind of controlled the few times we had to skip a day or two, but that's basically what drove this. The warmer weather, fortunately for us, last year the warmer weather tended to shift towards later in the year. We had a lot of rain earlier in the year, and then the warmer weather shifted. So we still got a lot of good warm days, and I wanted to show that here by a summary of the temperature. On the first column on your left is the noontime temperature, which is probably most relevant to when we're collecting the sample. But then I also wanted to capture the daily high and low just to give you a sense of the range. And so as you move down into, again, looking in October and that region, it was a fairly warm month. And we had the noontime temperature going from 63, depending on what region we were in, up to 103 degrees Fahrenheit. So there were some fairly warm days out there when we were collecting samples. The highs actually went up to 111 on the one monitoring event day, although we were trying to get out of the field by then and get back to the shade. But that gives you a sense of there is some indication that we wanted to be out there on warmer days because off-gassing from the surfaces. So we accomplished that, I think, across the board, even though the sampling itself may have shifted a little later than we wanted to. So on-field conditions, what did it really look like out there? And we did a lot of measurements, ancillary measurements, subsequent, in addition to the chemical measurements, we did a lot of measurements just to see what the environment looked like. Mostly centered around meteorology and things that force the temperature and such. So on the figure on my left, I guess on your left, looking at the screen, is a tower that we use, a stratification tower, to track temperature, basically starting at the very bottom of the crumb, looking at the probes in the lower center picture. So the temperature is measured right at the bottom of the crumb, and then somewhere in the middle of the crumb infill layer. Then moving up, we measured infrared temperature on the surface. So we got 3 different levels before we even get off of the grass or the turf surface of temperatures. And then stratified going up with distance, continuing to go up with distance. We measured temperature at different elevations above the field. And finally, we measured the solar energy input to the field to try and make sense of all of these temperature measurements. Those measurements, and following a theme that you'll see throughout the day, were collected in various levels of orientation. So we measured things from the ground up, and we measured things across space horizontally, and we also measured things through time. So we had these three different dimensions of measurements, and we'll come back to that as we present data throughout the... Oh, there we go. Broke the slide. Okay, this one shows a lot of information, so let me spend a few minutes on this. Upper left side is an indication, and this is just a typical field. We just grabbed this one out of the data set to try and show the interaction or the interrelationship between the things we're measuring. And we're going to overlay on top of this, all of this information, the chemical measurements as well. But to start out just by saying, what does the field look like? The upper left gives you a sense of the wind movement across the field during the day and during a particular monitoring event. And you can see as you read this, back, okay. And that's, as you read this, to the left of this first figure on the upper left of your screen, you could see that the wind speed is very calm. And when it's calm, you get a lot of variation in direction. And as the day progressed towards the end of the monitoring period, and it often happened, the wind would sort of develop and generate later in the day, and the direction would sort of stabilize. If you look down to the next one down, that's just a measure of ozone. And in this case, we're including ozone not as a pollutant, but as just an indicator of the environment. And you can see that the wind mass, the air mass tends to change as you move through the day. Depending on the direction the wind's blowing, things change. And so you pick up different off-field conditions that are coming across that field. So then if we look over at the temperature, and I'm going to start at the bottom and work my way up, the temperature probes on the bottom right were inserted deep into the turf, and basically it hit the bottom of the turf crumb infill layer, the first probe. So that upper line, I guess if you look at the blue line is generally throughout the day is the cooler of the lines, and as you move towards the surface, the very surface tends to be the hottest place on the field because of the solar energy. And you also look at, we've got on a secondary axis there, the insolation, which is the solar input, the energy input into that field. And the temperature of the field tends to track that. Moving up to the upper chart, we see the stratification of temperature over the field. And you can see as you move away from the field from 8 inches to 24, 45 and up, you fairly quickly approach a fairly constant, well-mixed environment. So the temperature tends to approach what you would measure at a local met station nearby. So it does tend to approach the background fairly quickly because of mixing. So I want to talk a little bit about the wind because the next chart's going to probably cause seizures. The wind speed I want to convert into just a single picture of each field. And so doing that, looking at just direction and speed, we can capture that all in a windrose. Just very quickly for everyone, the windrose is essentially, in this case, it's designed or built showing the wind direction. So a longer bar pointing in one direction is basically a more percentage of time going in that direction. And then the color of the bar as you move out is the wind speed. So you can kind of just, at a glance, once you get used to these figures a little bit, you can kind of see the general air mass, which direction and how fast it's moving throughout the day. And I wanted to give you a sense of that because then the last meeting we came to, the half of the fields that I had already done or we'd already accomplished, I had put the net or the experimental unit in exactly the opposite place that I wanted to. But we got better at that as the season progressed. We still had to predict in advance where that wind was going to come from, and we generally did a pretty good job. So the green globe that I put on the windrose gives you a sense of where we placed that experimental unit throughout the day. So now this chart, the goal of these large matrices that kind of show you all of the fields at a glance is to give you, just to give you a sense of the variability that we captured in our data set. And then you can actually go through and assess these individually, like the second in from the upper left shows a very constant, relatively high wind day, and the experimental unit was basically where we wanted it, downwind from that. There were some others that we still did get a little bit off, but Note that the color of the bars is wind speed, and so a lot of times the wind's going lots of different directions, but it's not going very fast. And so we did get a nice stable day to collect measurements. There are a few missing data points here. Things happen in the field, so when we don't get all the windrows data, but we do have some, essentially we did things in replicate almost every time. So in this case, this figure is, it captures a single location on field, and we've got multiple locations. So we'll finish populating that database as we move forward. This is just for your initial glance of the variability that we see. I wanted to also show that the solar insolation measure that we did, the energy hitting the field, the picture on the left-hand side shows you how we measure that. It's just a simple device we set out that measures watts per square unit of area. What's interesting about this data, again, we have a few missing datas, and in this case, that is truly missing data because the instrument wasn't available or had broken in those days. But what this does show us, in addition to sort of the range of energy throughout the season that we captured, but it also shows cloudy days and clear days. So we've got a lot of different dynamics going on in the field that these things show, and you can relate these all back to the results on individual fields. I've already showed you that stratified temperature. I wanted to expand that to all the fields now so you can have a sense of the range of temperatures that we were working in. And the difference in, on a cloudy day, you get temperatures that elevate and come back down. So it was a very interesting and fairly rich data set to show differences in the field. We took ozone out of one of our stratification sort of selection criteria, but we still did capture a wide range of ozone environments, and there was some conversation early on that higher ozone may interact with the crumb and alter or change the aerosol resuspension, different particle dynamics and such. So I just wanted to show that we did capture a wide range of ozone conditions, and this is just during our sampling days. So we had this measurement collected in sort of the center of our sampling unit, and we can track that. We rolled this idea out sort of late in the game, but we were able to go back and assess the fields. But the idea here is we were seeing a lot of variation in the surface itself. And that's what we were studying. We were studying the surface of this synthetic turf. And so we wanted a way to very systematically capture that variation. And I think it's a lot better. I'm hoping it's better on your screen. But what these are high-resolution images that are taken in a, it is, okay, good, that are taken in a portable studio, essentially, in an LED-lit studio with a uniform card. We always had this color card in with the crumb and allowed us to color grade these images. So these images are quantitatively comparable. You can look at one and look at the other, and it's not just an artifact of the daylight or the time of day or who took the picture. They're all color graded, and in a way we can look across them and see, age, the amount of crumb, the difference in the overlaying turf, the thickness of the material over the top. So I think they're fairly useful pictures, but this picture itself, although the audience doesn't get the sense of that, it does also give you a sense of the variation in the material that we tested or were able to get to. This shows
Randy, if I could just interrupt for a minute, I just want to make sure the audience also knows that, and the webcast, that these slides will be available on our website, so they can look at this themselves.
Fantastic, yeah. So on this image, we used the same technology. So these are also all color-graded images that give you a sense of, a clear visual comparison between the material. And what it shows you on the left-hand figure is the matrix of all the fields we tested, essentially the composition and size of the crumb. It gives you a good sense, I think, of, is there sand in there? Is there other materials in there? Is there junk that shows up with the material? The figure to the right on the screen gives you a sense of variation in density. So as the fresh material direct from the manufacturer is included here as a reference in the bottom left of this matrix, and then from the field, and we have these samples in front of you that you could pass around and take a look, but from the field themselves, essentially this is the same mass of material. So how far it fills up that little vial in the picture gives you a sense of the density. The stuff that's not filling as much has already compacted or has more dense material in it. So again, it's a nice way to look at the variation across all the fields and what we actually measured in the field when we got there. So this matrix, following the same theme, it's a visual comparison, but it's very quantitative because the images themselves have been standardized. So just visualizing what the conditions at the field might have been. This, in fact, is a PM 2.5 measurement on a glass fiber filter, high volume measurements that have been essentially clipped down. We didn't clip the filter, but we clipped the pictures. Just to show you, this is all off-site measurements to show you the range of conditions that we saw when we went to the field. So some of these may be closer to a freeway than others. Some of these may be out in rural areas, whether it's dusty or not. And so it really captures, if you just glance across that and look at the different densities or darknesses of those filters, it gives you a sense of the conditions in the field, regardless of where they might be. Thing go. Click the middle. Okay, so it'll run now. So I want to talk about the human factor now. And this is just a video clip that kind of gives you a sense of what we had going on. But overall, in summary, we did recruit up 74 different players that came out, and this was a human subjects approved protocol. So we followed the scripted the idea on how do you recruit and fair and uniform way. The 74 players participated in 122 events or 122 times. So that's about 3.5 players per field. Sometimes we had a few more, sometimes a few less, depending on how the recruiting went. And the experience range, it was really interesting that we had we had one young guy show up in cowboy boots and worked his tail off, and then we had actual professional soccer players out there doing things that I just couldn't imagine doing. And so it was a very broad spectrum of talent that we had out there. And in general, what they did was interact with this ball kicking machine that you see. The ball kicking machine was used to kind of get the pace right. So about every 10 seconds, a ball was launched to land somewhere towards the front of the net, and it was up to the recruited player to do whatever they wanted with that ball as it came in and use it for a little while and then kick it back to the machine. So you could see the activity that goes on. This is just one example. But you could see that clearly there's turf. The energy driven into the field is clearly resuspending the large crumb material, and it gives us a chance to, like right there, you could see in that video. So there's a lot of activity going on there, and then we're sampling all around that experimental unit, not out in front obviously, but on each side. This little image here happened on a day after a rainy event, and our kicking machine failed us, and so the players were very happy to go out and improvise, and so we let them improvise, and they set up and worked real hard for the rest of that period. So I hope that kind of gives you a sense of what we wanted to get, what we did get, and now we're going to start talking about the results. And I think we're going to move to Dr. Woody Delp next to talk about particles. We got that's the video. Sorry, on the upper black box is a failed. That's a missing data on the matrix. No, that was right outside that's a diesel exhaust right there, yeah. No, that was a missing data on that filter. We didn't get that picture. Yeah, so yeah, that's what that is. The other one was a video. So anyways, I'll introduce Dr. Woody Delp. We'll talk about, start talking about results, and it just keeps building and getting more and more detail and data rich, so we want to kind of ease into that. And then at the end of this section, I think we're scheduled for the end of Woody's talk. So, over to you.
I don't think there's any easing into the data that I'm going to show here because we've got quite a bit, and it's going to be it can be data dense. So, can you hear me? So I'm going to just go through the particle data itself, sort of a preliminary look at the particle data. And I didn't have the pleasure of going out into the field with these guys, but I've had the pleasure of playing with the data, and it is a rather deep data set. And so I think by now we understand a bit on the sampling strategy. We were looking mainly for the temporal variability. Did we see anything change during these kicking events? So we had a sampling period beforehand, kicking, and a sampling period afterwards. We're also looking generally for spatial variability, on, off the field, up, down. So we need to go through the particle instruments that we had here and then some results. And I'm going to have to go through things fairly quickly here. So what I just mentioned for the temporal variability, we would show up on a field on a particular day, get the instruments set up and running, and then essentially do nothing for an hour to allow to get background concentrations. Then we would start the kicking activities, the scripted activities, and that would run for the 3-hour period. Then we would have another, quiet period for an hour afterwards. Showing the net picture that we've already seen. So we had carts on either side of the net, as well as a cart directly behind the net and a cart well off of the field. And that would allow us to deal with our various, and the vertical stack, our vertical monitoring was accompanied with a cart directly behind the net. We're calling that one cart 2. So carts 1 and 3 were off to the side, and cart 4 was well off of the field. So for our particle instruments that we use, some of you are familiar with these, some of you may not be. We used an APS and an optical particle counter to deal with sizing issues. And an APS instrument is called an aerodynamic particle sizer. It gives us 52 bins of information in particle sizes from 0.5 micron up to 20 micrometers. It gives us 1 minute resolution. We just had it on the field, down low, just off of the turf. And its native units that it reports out are particle counts per cubic centimeter. The MET1 optical particle counters that we used gives us 6 channels of resolution. Now they are optical, so it's a very different measurement method. So sometimes doing A-B comparisons between particle instruments can be a bit challenging. But so we're going to focus mainly on comparisons with the same class of particle instrument. This one gives us 6 channels from 0.3 up to 10 micron, 1 minute resolution, and we're using this one in a vertical profile on cart 2 directly behind the net. We did particle mass measurements both on and off the field. So I've got an icon in the upper corner showing horizontal arrows going back and forth. If you see that elsewhere in the presentation, it means we're looking for information that may lead us to on-off spatial variability. And the stopwatch icon I have on there, hopefully we may be able to glean information from activities. So for our particle mass measurements, we had the availability of dust tracks for the first 2/3 of the fields that we measured. And then we knew that we were going to lose the dust tracks, and we had to go to these MET1 photometers for the remainder of the field. So we had some overlap between the two instruments. They are both optical photometers, but they operate on slightly different scattering angles, and they're calibrated to different particles. So again, getting the absolute A-B comparison requires a little bit of effort, which we can do. And then we also had a PEM sample, a gravimetric sample, using the glass fiber filters both on and off the field with a high volume pump. So this is showing a cart setup that was the cart 2 directly behind the net. And we can see the APS was setting on the field, and the sample height on it was roughly 9 inches above the turf. And I've taken and I binned some data here. So I'm showing you a set of bins that would represent larger size particles and a set of bins that would represent smaller size particles for a particular field. And we see that there's changes during the kicking, but it was starting to change in the period beforehand. And it's different period after our post-kicking than it was a pre-kicking. So getting some of the time information as far as the temporal variability, we're going to be looking at things that are going on in this gray band in between. Now, if we use an APS, we can also get what a lot of particle scientists are used to, normalized particle distribution. So it gets you an idea of the range of particles that are out there. And I'm just building up what a particle distribution looks like here. So if we use all 52 of the bins, we take a slice here at the one point in time, we get a particle distribution that looks like the one that we see on the right-hand side. Take another slice, we get this, and we take another slice and we get this. So things are a bit different post-kicking than it was pre and during the kicking. Is this environmental or is this on field? We're going to have to dig into that a little bit. Now, this is a very busy slide. This is showing the normalized particle distributions across all 35 of our fields. And what we're basically looking for on the left-hand side is the particle count distribution. And on the right-hand side is a particle mass distribution, assuming a unit density of the particles. And a brighter color indicates more particles in that size. And the size is determined by, on the y-axis on each one of these little grids, shows you the particle size going from the 0.5 micron up to 20 micron. And roughly halfway across one of those grid plots is the 2.5 number. So on the lower part of that would represent respirable particles, and the upper part of it would represent the larger particles.
Each one of these swatches is a separate field, is that
Correct.
Okay.
Correct. So that's a very, very busy plot, so maybe we'll look at that later on, if you're tired at night and want to pop open the slides and look at it. So we can look at some spatial variability here. Our real-time measurements with the dust track and this MET1 gave us a pretty good opportunity to look at the spatial variability. Well,
Can I just ask, why did you have to switch from the dust track to the MET1?
prior commitments for other projects.
Okay.
Yep. And we can look at some of the on-field, off-field with the PIMs. Again, Randy showed you the same grid picture earlier on the off-field. Now this is overlaying the on-field and off-field samples on the same plot. And again, these are color graded. We can get some we can quantify the numbers here, but we also know what the masses of these filters are. And so you can see on the really dirty filters that were collected, it's indicating that there was, a lot of, ambient particulate matter in the air, and this was a 2.5 cut on it. But we also see some where, there's not that much difference between the on and off field from a visual point of view. If we use one of our, I'm going to click too quickly. So this is using 3 example fields with our MET1 instruments. And on the far left, we can see the scales are different on each one of these. On the far left, the way it's making these changes, we see these distinct bands. It's actually a very clean environment. It was a clean field. And things were coming down to becoming even cleaner during the kicking activity. The middle figure here shows that things were changed and dropped down in the middle of the kicking activity, came back up again, but we were seeing roughly the same on or off the field types of responses from the instrument. And on the furthest, on our right here, that figure, it was quite a dirty day, and we see things that were gradually increasing throughout the day. And we see the same rough numbers on or off of the field. We take all of the data and so I took all of the data that was available using all of my PM 2.5 instruments, and I did hourly averages on the real-time instruments. And so I had 5 different potential averaging periods. The 1 hour for the pre-kicking, I had the 3 different hours for the kicking activities, and then I had the 1 hour for the post-kicking. And I'm plotting here on the off-field measurement is on the x-axis, and then the on-field measurements are on the y-axis. And what the 1-to-1 line is shown in the middle, and then I've got a gray band here that's representing a plus or minus 25% band from that. And for the dust tracks, I was getting a little bit of variability where it's showing that it's perhaps a bit higher, somewhere in the, a little bit to 25% higher off the field than it was on the field. Using the other instruments, we don't quite see that same behavior. It looks more like they're much closer and clustered around the 1-to-1 line. We move on to a particle counter, another particle counter instruments that we had, our met one instruments that were on the vertical stack. We had one at 18 inches above the deck. We had one at 35 inches, and we had one at 60 inches. This is showing the profile for a single bin, the 0.4 to 0.5 micron size range for all of those. And we don't have anything for the one grid there, but all the others we do. I mean, we also are missing a couple of, because as Randy said, this was out in the field. I think one of the instruments got kicked one time, so we lost data for one of them. But for the most part, we see a slight trend in the numbers. You know, at this point in state, I could say that it looks like the numbers are slightly higher down low than they are a little bit less as we move up on the stack. And taking that same one-to-one approach, so I've done an hourly averaging on the numbers, and this sort of shows that for that same particle size bin, the 0.4 to 0.5 micron, that at 60 inches up, they're approximately 25% lower than they were at 18 inches. If I look at all the size bins from that same instrument, we see that behavior on the smaller channels, but not as much on the larger channels. And if we take the same instrument, you can come up with an estimated mass if we assume spherical particles, if we assume a density with it. And I think I did assume the density of 1.6 grams per cc, which is what people use oftentimes if you don't know anything about the stuff that you're dealing with. But I see the same sort of trend that, you know, the estimated mass would show that with this, that it's a little bit higher down at 18 inches than it is at 60 inches. I'd like to close out with this, that we clearly see we're moving stuff around. Randy's.
Those aren't my feet.
Yeah. I'd hope he's washed them since then, but the videos also clearly showed that the crumb was being moved with the kicking. You know, the player's feet here showing that stuff was definitely moving around. But it also on the little pictures of the trays of the crumb, you know, this crumb size is pretty large from an aerosolized point of view. And we're talking about stuff that's probably in the millimeter size range rather than, you know, a respirable size range. So I think that's moving it on.
If I may, I think
You
we
may.
need to just repeat that point for people who maybe are not hip to the lingo here. Would you like to do that, or would you like me to try to do that? Because I mean, I think maybe I'll try to do it. That these particle monitoring gizmos are measuring small particles of the size that might get into your lungs, and are relatively. It's the smaller part of particles that come up in the air, and a lot of the crumb rubber is bigger than that, and so you wouldn't expect it to be picked up here necessarily, correct?
What's generally referred to as respirable size ranges is 2.5 micron or lower. Our instrument, we had instruments that were measured. Okay, deep recesses. We'll get things in the upper. Okay, sorry. Okay, we're measuring up 20 we're measuring up to 20 microns with the APS at the on-field. We were using the OPCs that would give us size information, size resolved information. Now the largest bin goes from 2.5 micron to 10 micron, and our gravimetric samples had a 2.5 micron cut on them. So we're measuring things that would cover what are common respirable ranges. But so you're correct in that what we normally think of as the largest risks are the smaller size particles, which is. Sorry, I don't
correct you. Respirable fraction is 10 microns and less. So between 10 and 2.5, you get deposition below the vocal cords. And for somebody with asthma, what deposits on the airways is actually very important. But you know, the size that gets into the alveoli, the deep lung, is 2.5 and less.
And if I may, but my point is that I think could be obscure to people who are not hip to this whole discussion, and I didn't mean to get into the respirable argument, only into we're measuring relatively small particles that we think about when we look at air pollution, and not the bigger particles, which could also be bouncing around as we saw in the video. So we don't want people to think that we think that there's actually necessarily less particles on the field, because we're only measuring very small ones, compared to elsewhere. And the very small ones elsewhere could be because it's a parking lot, right? So, I think that this is a very elegant presentation, and I appreciate it, and I think I got most of it. But the way you talk about it excludes those non-measured larger parts of the crumb rubber that are also flying around. And I just wanted to bring that point out for people who may not have studied this as much.
So with that, I'm opening up to the panel for any comments or questions. Dr. Eckel.
Excellent. There we go. Thank you. Okay. So again, data is very exciting. I'm very excited. So I have a couple questions to start things off. I really like the stratified sampling design that you have, the randomized stratified sampling design. And that's a really strong design for getting representation of the fields across the state. So I think that's excellent. And you did mention a little bit, especially for regions 4 and 5, which I understand it was very hard to get samples and there's a small number of fields to draw from. You mentioned a little bit that it was hard to get owners of fields to agree to participate. I was wondering if you could comment a little bit more on whether or not you actually looked at potential non-response bias or people refusing. Were there certain characteristics of field owners who didn't want to participate, to give us some sense of how generalizable this sample is? Even though it was a randomized design, some people chose to participate, some people didn't. That might be something to look at in the future.
Definitely. We haven't get to that, but we did just kind of bring back our memory when we recruit. There's a lot of public entity refuse to, or they don't have time to participate because the field usually are very highly frequently used. So we have to respect people who does not allow us to go. I don't remember any specific pattern, especially most of the field are very expensive. They're owned by schools, city, not individual kind of mom and pop shop. So they are all kind of public field that community field we sample. In our database, we have only field that are go through the process of care recycle to get the funding, or we have the biggest installer who provides the database. So these are all community public access or school access kind of field. We will definitely look at the data when we get down to that level.
Thank you. And let me ask just a few other kind of brief questions. And these are sort of outside my area of expertise, and so others might comment more on this. But at one point, we had the beautiful wind roses, and you mentioned the location of the sampling unit. And I was wondering, was that the sort of the sampling units right around the net, and where was the off-field location relative to those? And
yeah, the green globe, the sampling location relative to the wind rose was what we call the experimental unit, which is kind of dictated by the net. So in a perfect world, the opening of the net would be facing into the largest, fastest bar. And we got close. I mean, we got close a lot of the times. The off-field, the sense that how well we did on that placement of the net also gives you a sense of how well we did on off-field, because we, in advance, decided the direction of the wind, and we would try and get the off-field upwind of the field, the off-field location, upwind of the field. There were a lot of factors that came into that. Availability of power was one, safety was one, security. We didn't want things leaving when they're not visually available to look at. So those things affected a little bit, but in general, the green dot, how well we did on the green dot is also how well we did on the off-field, because if we got the wind wrong, we put it in the wrong place. But in general, we did pretty good. So.
And then it's sort of a related question also. The sampling was 5 hours long. Did you try to always start around the same time of day? Because I know there's diurnal patterns in these exposures.
Within an hour? Yeah, I think we shifted roughly an hour over the course of the entire study, so we did try and start in general at the same time of day. There was a factor involved of, we wanted to capture the warm part of the day, but we also didn't want to overstress the subjects that we were using, so we tried to capture the active period sometime ending around noon in the most part, so yeah.
Great, thank you. And then one minor question is, it was on one of the slides you showed the pictures of all the samples, and I was wondering, is it possible to tell us which of those were the cork and rubber mixture? Because it looked like perhaps maybe there was sand or something, but some of them looked like they were mixed colors and some looked pretty black, and I know that there were two cork and rubber ones.
Yeah, the appearance of the sample we collect is very diverse. We have blades in it. Some of the field, the blades are broken down. Some are earlier, younger field, they still have broken down blade. Some are older, they have more debris. Depends on how well the field are maintained. We have leaves, we have all kinds of debris. But also sand, some of the field are fully rubber, some are sand mix. So we did hit a diverse spectrum of the infill we can see.
And my final comment is more on the statistical analysis. So I can see that we have really rich data within field, looking at this temporal and spatial variability, and that's very exciting. But I know with sort of this stratified, factorial design of sampling, I'm hoping that we can also do some across-field comparisons. I know our sample size is limited, but I'd be very curious to see some analyses looking at whether the age of the field has an impact on some of these quantities that are being measured, and also, region. I know it's going to be very hard to tell region 4 and 5 from the others because there's only 2 fields in that strata. But
yeah, definitely. That's the purpose of stratifying and getting the visual picture as well. We're going to combine all the data. Even within a region, sometimes there's a diversity in the geography. So we do have the location so we can compare and see like the ocean coastal versus the high mountain, different comparison.
Thank you.
Thank you, Dr. Eckel. I should have said at the start of this that staff would really like us to focus on the discussion questions that are above. They also welcome any other comments. I'm not chastising you in any way. Those were good questions, but I want to make sure that we do at least address the staff questions as well. So, Dr. Bennett, do you have anything you want to say at this point?
I did have some questions, but I don't have time to switch them to make sure they match the discussion.
Oh, that's okay.
I'm not that fast. I just had a question on the temperature distributions in October. It looked like that was the hottest day, but did you tend to have quite a few days in October that were sort of warm, like over 75 at noon, or?
I mean, we'll be able to say that with a lot of precision because we have the temperature data, but just qualitatively, yes.
Okay,
it was
great.
hot.
And then
it was generally hot.
I was slightly confused on the temperature distributions on the y-axis, because it didn't seem like they were absolute temperatures. It just seemed like...
Yeah, we wanted to show you trends without
Okay.
kind of muddying the water of getting in a conversation about a single field. So essentially, I wanted to really focus on the trends at that point.
Okay, great, thank you. And then on the infill density, is that, it seems like it would be interesting to see if the denser ones was correlated with the older fields. Is that something that you looked at or were thinking of looking at?
I haven't looked at that yet. We're looking in the chemical side right now, pretty buried in
Okay,
that. So
great, thanks. And then, I was curious on the concentrations being lower, or I'm sorry, being higher, closer to the field, especially given that some of these were the really small size fractions, and also that you saw the trend of being a stronger vertical gradient on these really small particles. And so are we thinking that there's like some kind of secondary reactions going on, or what do we think?
It's too soon to tell for sure.
Okay.
If there were secondary reactions going on, I would anticipate that trend to go down as we got into dirtier ambient air. So because then the secondary reactions that are going on that are the formation of the particles, you would anticipate to be closer to a fixed sort of like source term. And if we're putting a fixed source term into a dirtier blob of air, you'd
Right.
expect to see less of a change. So that's something is on our list to look into more.
Great. And then I'll look at these discussion questions and raise my hand again later after that.
Thanks, Dr. Bennett. Dr. Sheldon, do you have any comments at this point?
Yeah, actually, the visual data that you showed was very interesting, both Randy's feet and, no, and the ball kicking, when the ball hit the turf, and also when somebody kicked the turf. What I have seen with house dust is it's the much smaller particles that adhere to the skin, which was what we were seeing on your legs. Also, the much smaller particles tend to have a different chemical composition. And, I know this can add a whole new level of complexity. And I don't know how you reconcile that. But I think that there needs to be, given the human exposure, both inhalation and dermal uptake, some kind of consideration of what particle sizes are going to adhere and be exposed to most. The second thing was with the ball hitting the ground or the person kicking the ground, that seemed to be a very localized kind of cloud that went up in the air. And again, I sort of am a little reluctant to bring these things up because it adds a lot more complexity, because where you're monitoring is not close to where that is occurring. I think it provides very good and useful data. But how do we, it's a thing to think about and not to do, but how can, it's under this for the purpose of evaluating exposure. How do you evaluate that better? I don't have answers. It is very complex. Do you have thoughts?
Yeah, I appreciate you bringing that up, because our goal was to get the measurement of exposure concentrations as close to the receptor as we could, but for obvious reasons, we could not get closer than the outside of that net,
Right.
And still have equipment to
Other
work
than
with.
your feet.
So yeah, that's a very good point, and both points actually. The size issue. I mean, the visually seeing the crumb being stirred up is what is a really strong visual image.
Yeah.
But as aerosol scientists, I think we're fairly comfortable that those things we see are falling right back down to the ground, and they're not participating necessarily in the exposure pathway. But the smaller things that we don't see may be. And did we capture those, or can we relate what we did capture to what those are likely to be?
And just to clarify, the particles that you saw on whosever feet they were,
Yeah.
those are also big particles. They may have small ones.
But they are adhering to the skin,
But
which
they're-
provides an opportunity
Yeah.
for dermal exposure.
they're big.
Yeah. Well, they're not. They're not. Yes, respirable or inhalable, but they are what is there. Did you ever have people who were diving on the ground during this? They were just kicking?
That's actually an activity pattern. We did. Yeah, we had
Okay.
sliding and diving, and what do they call it when you go upside down and kick? I mean, they were just having a
Right,
blast.
right.
It was,
Okay,
and we
okay.
paid them to do it, and they still had fun.
But
It
of course,
was great.
that would reflect maybe personal exposure. It wouldn't reflect so much what's there.
Yeah,
because
so
that's
our
where it
goal was
kicks in.
activity,
Yeah.
energy into that
no,
surface.
I
Yeah.
understand, but okay.
In terms of the diving, my son was a goalie in soccer. It really improved his ability as a shortstop in terms of
There
diving.
you go.
No, not at this point. So maybe I'll start with Dr. McCone. Do you?
It's not
Okay,
going to
thanks.
his question.
So I'm going to focus directly on the questions, to help you out. And the first one, on question number one, there was one thing. So you said you reversed the windrows, right? Because typically a wind. in your presentation, you reversed, I mean, the standard wind rose shows where the wind is coming from, but and I know everybody gets totally confused when they see those because they immediately interpret it as where the wind is going. So I think that's a great idea for presenting this. But then on the other hand, you have to be careful. I think you have to put a warning there because anyone who knows meteorology or does air dispersion will say, these guys got it wrong. You know, they're talking about the wind blowing in, I mean, just to be careful.
Totally
It's a
appreciate
great
that. That was a
idea
mistake,
to do that.
And we
'cause-
couldn't fix it in time because as I put all the green globes on there, I'm like, I got them all wrong. This is crazy. And then we realized there was an instrument interpretation.
Right, so you just have to make clear to people what, because for those who know, it's going to be confusing. For those who don't, they're going to go, oh, that makes sense. You know, this is where the wind's going. Okay, minor. And then on figure 46, sorry, I'll take you away from the questions. But this is about the other two questions about interpretation and binning. So I thought I would, so figure 46 is the one with it's like this one or the other one. Or slide 4, yeah, this one. So when you get to this question of whether you can start aggregating things, so this is it's very interesting because, I mean, to me, one of the things I see in this, if I'm not overreading it, is as the PM concentrations get higher, you get a little tighter fit, right? And those are likely to be places, I'm guessing those might be places where the background is contributing a lot, because otherwise, I mean, those sites stand out. But I'm not sure it's because they're the dirtiest sites in terms of the emission from the field. So if it's possible to begin, and it makes sense, because you would see less variability where the levels are driven more by background, right? And you see a lot more variability down on the left, right, lower left, where the background is pretty clean air, so you're really picking up. And I think that might be something you can use to begin. It deals with this discussion point about, are there ways to aggregate fields? And I think you might take this diagram and see where there's sort of an inflection point or a change, where there's less variability or more variability, and start commenting about what that, or speculating what that might be. And again, I think it is background. I don't think, you know, from what you've seen, I don't know how the crumb stirring up the dust can actually suddenly stand out and go way up to 100, you know, near close to whatever that is, 50 micrograms per cubic meter. I think you have to be in an air district where that might be happening, or somebody's burning wood nearby or something like that. And I think there was the two, I mean, that one is basically discussions points 2 and 3, which were about better ways to aggregate among the different sites and then interpretation of the data. So I think this one is one that has some opportunity, and I'll focus on that one and not go anywhere else.
So before, no, could you keep that one up? 46. So the question I had, it follows my interruption during your presentation. So that the dust track Met 1, have you actually cross-calibrated? Thank you.
Have, and the slide didn't make the cut, but we had some attempts to do cross-calibrations using the gravimetric sample as the gold standard. And we see the deeper you always go with trying to compare particle instruments, the more, you know, it can be an exercise in frustration at times. I mean, we see different calibration constants, calibration coefficients that would apply for different fields. And so generally, as other people have seen, the dust tracks were reporting higher in the vicinity of around a factor of 2. I mean, it's calibrated to an Arizona road dust. The Met 1 instrument's calibrated to a PSL standard. It uses a different scattering angle, and it's generally closer to what the gravimetric sample is. But so, and the plot on this one is showing the as reported values. There was no attempt to do cross calibrations on them yet.
Thank you. Dr. Kyle? Oh.
One quick comment while we're still on the slide. One nice sensitivity analysis might be nice to see related to this kind of figure would be to maybe subset to those fields where you had the wind placement right, to see if the signal is stronger or just as an idea.
Dr. Bennett.
In terms of the equipment, I forgot to ask this earlier. Were the two dust tracks always the same upwind and the same downwind, and was there evaluation of the two of them side by side?
The same instrument was used in each location each time. And at one point, just got to come right out and say it, Randy's bad with instruments. He can kill any instrument. He killed one of the dust tracks that happened to
Oh,
be
he's the one that kicked it?
Yeah, he did something. We never do know why it happens with Randy whenever he grabs the instruments. But we had the one of the instruments went out about halfway through the period, and it happened to be one of the off-field dust tracks. And I saw the same response, with the two different dust tracks there. And we do have periods of time where they were located side by side, I believe, in a lab at LBL. And we haven't had the chance to go back and really look in detail at those side-by-side data points. But it's on my list.
Yeah, just for my own defense, I don't always break instruments, but we did purposely co-deploy all of the instruments in different conditions to try and get this cross-calibration issue worked out. So, yeah.
Dr. Kyle, thank you for being patient.
You're welcome. I have 4 kind of somewhat random comments. And one of them is just a presentation one, and it's the picture with the green dots. And I love the visual presentation of this, except for one thing, which I'll get to in a minute. But I wonder what this would look like if you put all the dots aligned in the same direction so that you could actually compare these. I mean, because I can't compare these in my mind because there's too many directions of the dots. So that's just a comment about how can we help to still yet another picture from this. And I agree with what Tom said about the wind rows, blah, blah, blah. So I won't go into that. Then my second thing is, this is a bigger question, but I think the presentation and this work has a little bit, I don't want to say obscured, but maybe not brought forward enough this issue of what we're talking about here, I think, is direct impact of particles that are relevant to respiration, right? That's really what this is trying to measure. And that's part of it, but there are other ways to look at it too. So in presenting this, I think you could just be a little clearer about what piece of this it is, because it's not really measuring necessarily the particles that adhere and take home, which I think are the larger ones, in contrast to the comment about the indoor dust. Maybe it's the smaller ones that adhere. The particles people are worried about are the ones that are still in their clothes when they get home, So, I mean, that could be true or false, but it's not what you're looking at here. So something about separating out different parts of this particle discussion, I think will be helpful to people understanding what you're talking about in different parts of this study that all sound a little bit the same, and they're not. Does that make sense? That's kind of an overarching comment. All right, and then my next thing is, well, how to analyze this. So you have all these pictures with all the fields, which are cool, but you don't have any pictures with all the stuff about one field, right? So you have all these pictures that show what you're seeing across the range of fields, you call it, which is actually just all the fields. But we're not looking at how anything is related for a field in here. And so that's what I would do next, is pull this apart and take all the slides for a few fields and see what that looked like. And until I do that, I can't talk to you about how to aggregate, because I can't see that next step. So that's my reaction. I don't know. And we haven't talked about exactly what your outcome variables are here anyway, right? I mean, how you're going to, assuming at some point there'll be some sort of multivariate model that you'll look at, what are the outcome variables to that going to be in terms of different things that you're representing visually here? That would be another thing. I'm sure you've thought of this already, but to try to distill and maybe share to help us think about, what's occurring to you as you've looked at this in this way, and probably other ways that you haven't yet shown us because it's not done, blah, blah, blah. So that's where I would go to try to figure out what to do about aggregating and further work. And then this is just a worry I have, and that is you excluded all the water, but what if water matters? Or are we sure that it doesn't? because you didn't want to get your instruments wet and everything. I understand all that, but there's some suggestion in some studies that water matters in this, and so I'm raised that as something that we've excluded here. Maybe it doesn't matter for particles, or I don't know, but that is one thing. So that's a question.
Yeah, it's a good question. We didn't necessarily exclude water. Wet surfaces were okay. We started often when the surfaces were still wet, and they dried throughout the day. We just excluded rain for the obvious reason.
Yes.
Tried to avoid that at all costs. So, yeah, so that's a good point, though, as far as the water, and that pathway is important. Often it's an ecological pathway and not a human pathway, the water runoff, but other studies are delving into that, I think.
Yes, so, okay.
So in response to the larger particle, I want to bring broader view here. The particle that we sample in the air are mainly to cover the inhalation pathway, but we also collecting sample raw from the field from multiple locations spread out in each field, and those are being looked at, and we will definitely cover the larger particle or a smaller particle from those samples actually. That is potential for thermal adhesion, for inhalation, ingestion pathway, even at that level. So we are not looking at it, but it will go as the presentation today. You will hear more about the behavior of these larger particles that are being analyzed. And also, we are also collecting relative humidity data in the field, so it does have an impact on how particles suspend, how the other behavior of VOC. So I want to make sure that is out here to be discussed as well.
No, thank you for that. And I didn't mean to suggest that it's not being done. It's just that the way this is talked about, I think is confusing about this is one piece and there's another piece over here. So, I'm trying to speak to our public audience too about how can we explain this in ways that tend to deconfuse rather than confuse. That's really what that came from. So thank you.
Appreciate it.
I did look through the rest of the materials. So.
Appreciate that.
Mr. Avil.
So I have several pages of comments, actually, which I will share with you in the interest of time, because I've been warned by the chair that we're trying to keep this moving. But I mean, addressing the discussion questions. So first, I think there's an important aspect of this that we all want to consider, which is that we want to have the technical details provided in the report so people can follow the information and interpret it. But we also need to have it in a way that's understandable by the public, that they can actually read this and get the information from it. And I think there are a lot of, right now on the materials that were provided in the meeting, there are a lot of inconsistencies in the report. And I'll provide you with the documentation, at least what I thought were inconsistencies that just need to be resolved. And so in terms of the presentations that have been done today, I just have a couple of questions. One is with regard to the age of the field and the exclusion or inclusion criteria. You spoke a little bit about that. You said that there were no fields that were included that were less than at least a year old. And I just raised the issue for you. I know we're not going to go back and sampling. And parenthetically, I just want to say I'm very impressed by the amount of sampling that was done, the difficulty to do these. So I appreciate all the work that is in the field to get this done. That notwithstanding, however, you did not sample any new fields that was less than a year old. And I just offer for you consideration that, in the indoor sampling world for air pollution, for example, one might be concerned with a sick building syndrome type thing where fresh materials outgas at higher rates until they reach some period of equilibrium. And I don't know that happens or doesn't happen on a newly deployed field, but I mean, it's quite possible that it could, and you don't have, we can't face that here, so we don't know. But there certainly are fields out there that are, within a year of age. So I just offer that. You made a lot of measurements with regard to temperature variation and wind direction, wind speed, and so forth. It would be useful in the report, if it's possible, to relate that to whether these are representative of temperature and weather patterns in the last couple of years, if this was an outlier type of year. I mean, how does this fit in the range of information? Is it, because people are going to try to take this and use this. And so the question is, how does it fit in with what we are likely to encounter in the scheme of things? And on the issue of temperature, while on it, I was sort of surprised. Anecdotally, we've seen reports about very high temperatures at the field, 120, 140 degrees. I've even heard from professional players 150 degrees on the field on hot days, and it doesn't seem. Again, it's a function of where you are in the field, but I assume because you're talking about the air temperature, even up to 111 seems like it's pretty low compared to the kinds of air temperatures that are seen, and that will relate to outgassing and potential chemical interactions. So I'm not sure how that gets played out, but again, it comes back to the description in the report as to how it's, how that information is relayed. Similarly, your video that you showed were very interesting, and looked like they were all men or young men that were doing that sort of activity that you did. And I don't know if there's a range of ages, height, weight, sex, et cetera, in trying to understand this, and if there are even different patterns of behavior. Maybe at the activity portion of it, we would capture some of that, but it's worth thinking about. Your particle size information is very fascinating, and there's going to be probably years of data to look at with regard to that. But I just would note that you don't have anything smaller than 0.3, and there's a lot of concern about smaller particle sizes. And the things everybody's been talking about, the things you can see and what it's 6 to you. I'm actually worried about the things you can't see that people breathe, and so I don't know how we do that, but I think that's an unmet need in terms of Patty's comment about where we go from here, what we think about what might be in the future. Because there's so much variability in terms of wind speed, wind direction, temperature, et cetera, field to field, it's hard for me to grasp how you're going to compare this across fields. And so I think Amy's exactly right. Some paradigm, whether we try to sort of refocus this and look at it from a different dimension, it's hard for me to think about how you compare this because they're all sort of unique individual experiments to look at the data. And in your description, you talked, and the slides and in your verbal description, you talked about larger, smaller, clean, et cetera, but those are not defined terminologies. And so if you're going to use those terminologies, especially in the report, I think you need to define that, because what some might consider large or small particles are very different depending on who you're talking to. And clean is a real problem for many researchers. And so I think we've got to be careful about how we taught that. And then again, finally, I think it's a little misleading to provide these plots. I understand why you do that, and I appreciate that the data is there, but I think it's a little misleading to have the plots of different kinds of instruments that are not cross-calibrated so that you're not comparing, comparing sort of apples to apples. It's hard for me to conclude, so are we seeing smaller particles or larger particles over this range, or is it just because the different instrument, how that relates? So if it is at all, I would encourage you to look at the gravimetric data from the PEMs and see if there's some way to sort of adjust these, or maybe even do a post-calibration of instrumentation, because I think often what happens is a factor sort of does move data up or down and may change the way we think about the data that's been presented. I mean, it's a tremendous amount of data and tremendous data set. Just trying to understand how to interpret it, I think, is an issue. Thank you.
Any, comments, Patty, before we move on?
Just a few quick comments to address Mr. Abel's comments. We did have sample field that are less than 1 year old. The reason it wasn't shown on the bar graph because that was the crumb mix field, and the bar graph wasn't for that purpose. So we did, in our database in the last year, there's no field installed in our database. We had updated. It's an indication that we don't know what happened, but we just don't have the database. So we did not sample any full crumb upper field with less than 1 year old, but we have manufacturer sample. Those are fresh from the tire being shed, and we are looking at those samples for VOC for all other chemical as a supplement. But also the cord field itself has crumb upper in it, and that one was only a few months old when we get there. So we're hoping that that can provide a little bit more on the data gap.
Okay, I think we need to move on to the next presentation.
Yes, definitely. Okay, good morning. Is this on? Yeah. My name is Hugo Esteliatz, and I'm going to describe, well, we have now two presentations on the chemical composition. My presentation here would be about the inorganic constituents of the infill materials. On the title, we have crumb rubber, and in some of the slides, you will see also crumb rubber, but the reality is the material we analyze is the whole infill material, which is mostly crumb rubber, but also has sand and all the other various materials that were mentioned before, and also all the atmospheric deposition. These fields have been out there for years, and there's a lot of other stuff there. So that said, I wanted to also acknowledge, let me switch here to the title slide properly. I want to acknowledge our colleagues from OEHHA, who actually did all the sampling on this, and also our LBNL colleagues, particularly Marion Russell, Sharon Chen, Jin Pan, and Wenmeng Dong, who did all the extractions and analysis of these samples. As an overview for this presentation, we're going to talk briefly about the sample collection and handling, then the three methods that were used to extract the samples, and then I will show results for about 19% of those samples. We are in the process of going through these many samples, and we have enough data now to show something that I think is statistically significant. And then we have some discussions at the end. In terms of the sampling, we in each field we had identified in general 10 locations, which were all over the field near the goal where you saw all the photos before, all the other equipment, but also farther away in the middle of the field, etc. So we kind of covered the whole area. In each position, there was an area delineated, which was about a square meter. And the material that was collected there was scooped with clean plastic material into polyethylene bottles. And those bottles were then staged during the rest of the sampling and then brought back to the lab. Fairly simple. And then at the lab, we store them in the dark under ambient temperature and humidity conditions. And from each of the samples that were analyzed, we took fractions of about 3 grams each that were placed in the plastic bottles that are shown on the photo, which are the same plastic bottles that you have there on your in here for to take a look later. And those were labeled separately with blind codes before the analysis, and the analysis was done by ICP-MS, which is inductively coupled plasma mass spectrometry at LBNL. So briefly about the 3 extraction methods that were used. First method was the EPA 3051A for total digestion. This method essentially characterizes the total content of any particular inorganic constituent and can be used for calculating oral bioaccessibility. Second method is ASTM F3188. In this case, this is a specific method designed for synthetic turf and in the situation in which it is ingested. So it tries to simulate the gastric condition. And again, this data is appropriate for oral bioaccessibility calculations. And the third method is one that we developed here between our team and OEHHA, and it was presented and discussed on the previous meeting, so you probably remember. We had a couple of presentations about this. We used biofluids that were developed from information in the literature that are commonly used in pharmaceutical testing and that simulate physiological conditions. And again, this method is applicable to the same oral bioaccessibility measurements. So more details about each of those methods. In the first one, the EPA method, it's a microwave-assisted digestion. We used a 0.1 gram of each sample that was dissolved in a mixture of concentrated nitric and hydrochloric acid. Then the extract was heated to 175 Celsius for the ramp was about 5.5 minutes, and then it was digested for about 10 minutes and cooled overnight before being filtered and diluted. And we use different dilution factors, considering that zinc is element that was present in a fairly high concentration had to be diluted further, and then another lower factor for the rest of the elements. Mercury is an element that had to be treated separately because there's a well-known problem with stability of mercury in this sample, so it has to be a gold salt has to be added to the extract before being processed to stabilize mercury by oxidizing it to a cation that is stable in solution. So that additional step was done for mercury, and then we had a separate round of measurements for mercury itself. On the ASTM method, again, this is specifically for metals in synthetic turf that are ingested, so it's a very applicable method for what we are looking at here. The conditions of both extraction times and temperature and pH, all of them simulate the digestive process. In this case, we also use 0.2 grams of each sample. In this case, added to 10 milliliters of a much more diluted hydrochloric acid at about pH 1 or 1.5, shaken for about an hour at 37 Celsius, and then staying just holding for another hour at the same temperature before extracting and filtering. The dilution factor here is lower, only 10, because as we will see next, concentrations are lower in this method. Also in this case, mercury, for the reasons mentioned before, mercury had to be treated separately, differently, with a gold salt in nitric acid just to preserve the mercury before analysis. Finally, the third method is our simulated saliva, gastric fluids, and intestinal fluids. Here we used a slightly larger amount, 0.5 grams, added first to 5 milliliters of artificial saliva buffer, incubated for 5 minutes at 37 Cs, followed by an addition of 20 milliliters of simulated fasted gastric fluid, which was further incubated for 2 hours at the same temperature, and then an additional 20 milliliters of fasted intestinal fluids, which was also incubated overnight at the same temperature. Everything else felt same treatment as the other extracts after that, filtration and analysis by ICP-MS, and in this case also mercury was treated the same way. So here's the status of the analysis to date. We are talking about a total of about 400, a little more than 400 samples from the fields. And also we have samples from manufacturers. These are 4 different manufacturers that provide us with crumb rubber that we call it pre-installed. This is material that has never been in the field. So we have all of our samples that have been analyzed so far correspond to all of the fields we have been to and also all of the manufacturers. So the details are shown in the table. We have, for 3 fields, we have measured all 10 of the samples that were collected. For 4 other fields, we measured only 3 of the samples that were collected. For 3 of the fields, we measured just 1, but we did twice. We had a duplicate of the same sample there. And then the majority of them, 25 samples, we analyzed only 1 of the 10 samples in each of them. And then for the manufacturers, we just did 1 analysis for each of them. So that's a total of 77 analyses, both on the EPA method and on the ASTM method. So we had done the same and each of the samples on both methods. So that amounts overall to a 19% on the bar on the bottom. That's our current status. 19% is enough samples to start looking at trends and what we find, and perhaps making decisions on how to proceed, whether we need to measure all the remaining 81%, or should we maybe look at some things in more detail. So there is a lot of information in these slides. I'm going to take some time to go through it. We have here the average of all of those samples that were already analyzed. On the top figure is the EPA method, on the bottom figure is the ASTM method. And we go from those that are in the highest concentration on the left to the lowest concentration in the right. The concentration ratio, well, the values are the average, and the error bar corresponds to the standard deviation for the whole 70 samples. And then the concentration range is, as you see, between 6 and 7 orders of magnitude in both of them. So the analysis covers really a wide range of concentrations. And what we did was we color-coded a few of the analytes that are of particular interest from the toxicological point of view. And those are also useful to guide the eye. If you want to compare across the two methods, you could see that easily that the order in which they come up in terms of concentrations is not the same. They are roughly the same, but you will see that some of the elements are extracted, relatively speaking, more effectively in one method versus the other. We have zinc there is at the top of the list on the EPA method. That's certainly our the highest concentration we measure here, which is in milligrams of zinc per gram of infill material, as mentioned, because this is an important constituent of the rubber itself. It's a catalyst of a vulcanization process, and it is well known to be present at high levels. For mercury, you will notice that mercury is on the other extreme, is one of the lowest concentrations we measure on the EPA method, and we have an asterisk on the ASTM method, and I'm going to talk about that on a couple of slides from now. We don't provide a concentration for mercury on here. Now, when we start comparing between the methods, the first thing we could do is to take a ratio of the concentrations and see, in all cases, we saw that the ASTM method provided a lower concentration than the EPA method, but for the majority or almost all of the analytes of concern, I would say that the ratio is about 5% or lower, which means the ASTM method extracts really a much smaller fraction of those elements than the other comparison we have done is between the ASTM method, which intends to simulate the gastric fluid or extraction in the gastric system, with our own approach to simulate also the gastric and intestinal fluids. In general, the oral pathway, we have both saliva and gastric and intestinal fluids. So this is a much more limited comparison. We are talking about here 8 samples only instead of 70. But the results are, I think, very convincing. We see that with a couple of exceptions, so outliers there, the vast majority of the elements really fall well within the 1-1 line. And you could say, okay, but this is a log-log plot, so what about the linear plot? So we did the linear plot too, which is here. And on the linear plot, on the linear plot, we see that the one line there is where we expect to see, obviously, ideally, we would like to see all of the analytes falling there, but we see the vast majority of them are not far from that if you consider the error bars and everything. So again, for the analytes of concern, I would say all of them, perhaps with the exception of arsenic, which is a little lower, are all in the right range. With respect to mercury, what we can say is that mercury is at a very low concentration in both methods, and we have here that square, that orange square is our method detection limit. So essentially what we see is that for the ASTM method, if we do look at the cumulative frequency of our results, the majority, almost all of the data fall below the limit of detection. So it's hard really to quantify, you can't really quantify for comparative terms with the EPA method, for which we have, on the contrary, a good quantification, even though these are really low levels. And finally, what I have is a set of 6 slides which look all the same. We just change the element on each of them, but you will see on all of them we have the EPA method on the left, the ASTM method on the right, and in each of them you see 4 data sets which correspond to 3 different fields, A, B, and C, and then the bulk, all of the samples integrated in just one figure. So what we show here is, and again, if you look at the units are different, so we're not comparing levels between one method and the other, we're just comparing the distribution. We have in each of the fields there, we have all 10 data points, and you will see that the majority of them, all of the data points fall well within the 1.5 of the interquartile distribution. And then, of course, when you look at the whole set, the all tested sample collection of data, we have a larger number of outliers over there. So this is for arsenic on our first slide, and let me show you now for cadmium. Fairly similar trends. We don't see, when we switch from one method to the other, the actual position of the box plots shifts, which represents clearly that not all fields are the same, but they are roughly within really the same ballpark, I would say. This is for chromium. In this case, we have all quite similar results for all of them. For manganese, same thing. There is field B seems to have a relatively higher in the ASTM method for most of these elements, but this is nickel. Again, very tight distribution on the EPA method. And finally, I think we have lead. A similar description here for lead. And finally, we have our discussion questions.
So it's time for panel comments, and just I would ask the panel members to look at the questions that staff has put up for discussion, but you feel free to say whatever you feel like. I knew you would do that anyway. Tom.
Well, I'll just start with, I'll let other people go into details. I was, in terms of just communicating this, if we could look at like 64 and 65 and some of the other slides. So let's start with like 64. I actually think it would be useful to start with one order of chemicals, whether it's the EPA method or the ASTM, but I would keep the same order of chemicals then, rather than doing the highest on left to right. You could start with one. It gets hard to really track the shift, particularly when you go to the next slide, 65, and now we have a whole nother order of chemicals. So, when somebody's trying to track this, you just have to go down to the bottom line and go, well, wait, what chemical it is, where did everything, and so if you keep the same order, at least people can see what chemicals are where and have a kind of a memory, and then can make that comparison more easily. Also, and again, this is more in terms of communication. So I do the same thing in slide 67, keep your order. And then for slides, that set of slides that start with 69, those are different scales, right? And I know you rescale it because it's hard to see the spread, but again, it would be useful if it was the same scale. You would probably see more. It's hard to interpret how close these actually are, because like here, for example, it looks like the center point of the scale is 5 microgram per gram on the left, and then 10 to the minus 3 microgram, 5, 10 to the minus 3 microgram per gram. Right, and so my brain can't really shift enough to see how close those really are. Okay. I have others, but I think I'll just pass on so we don't all ask 5 questions and then. Oh, sure. I'm sorry. Yeah.
Oh, well, no, I thanks for the comments, and I agree that the reason why we order them in decreasing concentration is just one criterion. The idea for those plots was to show the range of concentrations and the fact that you had more or less continuous distribution of concentration of constituents. I didn't mention the fact that the vast majority of the elements that were on the left side, the higher concentration ones, are most likely related with the sand or some of the more inert fractions that are not so relevant from health point of view, but it was interesting that those were grouped at that level. So the only, except for zinc, that is an ingredient or constituent of crumb rubber, we have that majority of the analytes that were of health concern were from the center to the lower range of concentration. So, I mean, I thought that was interesting to show, but I agree with you that if you want to start tracking one particular analyte, it's easier to have them all.
Can I just a question? I think you might have said it, but it wasn't clear. The ones that are gray on the, I'm sorry, on 64. Let's go back to 64. The ones that are gray, I mean, there's some in color and then the rest are gray.
Exactly, right.
That's
So
the
we
ones
use
that
the
are-
color coding in a way to help guide the eye. So if you're interested, for example, on say
Right.
lead is on brown and it's right there, and then you
like
look
calcium,
you look
nobody's
for
gonna-
it down
nobody's
there,
gonna
and
worry
it's
about it,
relatively
yeah.
easier to find it. I know it's 31 different analytes, so it's kind of hard to plot them one way or another. But I agree that that's a very, very good idea for,
I think the ones that are colored certainly have a standard. I mean, something like nobody's going to worry about, right, calcium. exposure to
and those
calcium.
are, you see, calcium, aluminum, iron, silicon, potassium, manganese. All of those are mostly on the left side. Those are really high concentration analytes. And then the ones that we will be mostly looking at are from the center to the right. But again, it's one criterion to plot, and you're right that we could possibly on the report, I think we should probably also tabulate all of this. And when it's tabulated, you should probably go by, say, atomic number.
I would like to interject here. I think I want to bring it up. This is the preliminary data, and each graph has its purpose, and I understand it's hard to gauge what's going on with 31 chemical. So if you don't mind, I would like to bring it back to the box and whisker plot, because there's a question really oriented around it. The ESCP method has a lot higher concentration, so we cannot bring it at the same scale as the ASTM method. But what we are trying to show here is we would like the panel to look at, for each field we have fully analyzed. The first 3 boxes on the left side of mine on the screen, they are fully analyzed, and for each metal that potential of concern, we would like to look at the distribution. How tight is it? It represents within field variability. And we are aware of this variability across field. And we want to see the panel's opinion on within field distribution here. That's the reason we on purpose not giving the full scale or everything, because we want you to see how tight the number is within the field. And there's a question associated with it.
Dr. Kyle?
Thank you. So the graphs are mostly about what method to use, but the questions are not. So to me, there's something missing here about looking at what the data looks like within and between fields to help you make this decision that you didn't do. And I don't know which method you should use. And I can't figure out these graphs on different scales. I can't understand them. I'm with Tom, only maybe worse. So I can't give you any feedback on that. But I don't know, you didn't, maybe you would analyze it using either method and look at the distribution within and between fields and see what that looks like, and then that might shed some light on whether you can combine them or not from a statistical point of view, rather than picking method point of view. That's a different question. Okay. That to me, that I don't see what basis you gave us to answer that. So maybe that's because I don't understand. I can't read the graphs on different scales. So those are my comments.
So the different method here, we are serving different purpose. The EPA method gives us what is the total content in the rubber. So that's the baseline what we're trying to look at. And then we have 2 different buffer here that we are trying to compare. So one of the questions is between the 2 different buffer, more physiological relevant buffer, how they behave. So we have the bar graph there between the 2 methods. And then the next question is, if we use one of the buffer, here is the behavior within field where we show the box plot. So hopefully I'm clarifying a little bit about the presentation, but definitely we see your point here. Appreciate it.
But then why would you choose one method or the other? they're answering different questions. It's still, I'm still missing this, I guess.
Can I make some comments
Yeah,
on
yeah.
this? When we started out, either it was the last meeting or the meeting before, there was a question of just doing bioaccessible data. And we said, well, that's probably not a really good idea. You need to do some total, because a lot of the data we showed with bioaccessible just showed nothing. I think your goal is to look for bioaccessible data. So I sort of think that you could, seen as you are detecting enough, that you could probably just do the bioaccessible data rather than the total, because I think you're right, one doesn't know how to relate that total data to what you're going to do in your exposure models. Now, so that would be my vote. My other vote would be, I would go with the ASTM method, and the reason I would go with that is that you probably want data that's comparable to what other laboratories are doing. And it is an ASTM method. I think more laboratories will be willing to pick that up. And so therefore, that's probably the one that, that I would do. If you're talking about, then you're asking us the question also, do we just, lump all the samples from one field together? And again, I know a lot of this, yes, you could do every sample all of the time. It's very expensive, it's very labor intensive. You're coming down to the end of the study, there's a crunch, and where is it best to put resources? I think that my opinion is that people are running all over the field. You just don't have a soccer ball. Well, I had a 5-year-old that stood by stood there, and I eventually told him, I'll give you candy if you run. Great mothering technique. But people are running all over the field. I think you're trying to get a vision of what's on the field. I think it's okay to probably put all the samples together. What you might do is in 10% of the fields, do the individual, do some individual samples so that you do have some of that data. So I think those are the questions that you are getting at. However, I have one other place where, again, I would like to see a few more samples. Again, this goes back to the size of the crumb, and that's really what I was referring to, not for inhalable, but for some of these other particles. In some samples, I think it would be useful to fractionate the size of the crumb with one of the methods and see if there is a difference in crumb size range, to see if you're going to get dramatically different results with one size or another. So anyway, those are my opinions.
Thank you, Dr. Sheldon. Well, okay, Dr. Bennett.
I was looking at the bar charts, and it seems that in some cases, I wasn't totally in agreement that the range was small within an individual sample, but it did seem that sometimes you were getting a single high one, and I would think on the ones that you wanted to subsample and do more of the individual markers, I would think you would purposely select those from the ones that tended to have the higher concentrations to see if those are isolated points or if those are truly fields that have much higher concentrations, because it seems that there seems to be some variability on some of those. So that's the only thing I wanted to add on number one, because I agree you don't need to do them all individually, but I think some of those ones that have the single samples that are high, particularly on these, and the other thing, it's hard to tell, I don't know if the fields that are high in arsenic are also the ones that are high in chromium, so I don't know if that's possible to sort of see if those are correlated and then pick the ones that are higher.
We'll definitely have the data to look at it when we start matching data, looking at field age as well and location.
Mr. Avil.
Yeah, so I don't have much more to add except to note that, you sort of focused on quantity and toxicity separately, but I think, showing plots of quantity is probably not so informative because we have to interpret it in terms of toxicity. And so What I think we'd rather know, all things considered, is not that there's a lot more calcium than there is chromium, but how the chromium relates to what you've seen compared to what sort of the health, what is known about the health levels, concentrations. And so I think getting at that and being clear in the communication of that, I think would be helpful.
Dr. Eckel?
So just one final comment on question one. I think it's good to keep in mind, what are the research questions? What do we lose if we do pool all the samples? I think, one question to think about is most of the players probably are moving around the field, but there are a few positions where they do stay, like, a goalie stays more in one area. And so is that an important question or not to address? Just think about what do we gain, what do we lose from pooling?
You do have a goalie sample, don't you? One right in front of the goal. So then you might do 2 per field. I mean, I know that when we have done, again, with pesticides indoors, we find huge differences. And then all of a sudden you're like, so how do I combine this whole thing into an exposure assessment? And that is the problem. And so pretty soon you just average the data and say, but I do think keeping something extra for a goalie area is a good idea.
Oh, I apologize. I nodded yes, but the goal area in our experimental design moved all over the field. It depended on the wind direction, power, availability, things like that, if that's what we meant. Oh, when we actually collected it, we did. Okay, yeah.
One interesting when we go out to, that's the beauty part of this study, is we actually go out to the field and see people practice. And the goalie practice, they practice throughout the field too. They run around, and a lot of times they do drill in the field, not necessarily in the goal. So during the practice, they actually dive more than they are doing game. We interview people. So that come back to the question at should we separate the one in front of the goal box for analysis? I think we should give it a try, definitely. But also bear in mind that the exposure for goalie is actually more diverse than what we think when we go out to look at these games and see them running around. Interesting. And some people actually play multiple positions.
Mr. Avil, another comment?
So I think that's true, but I think we don't want to lose sight of the fact that during a game or during matches, for most of these children, adults, et cetera, the goalies are going to be in the goal box, and they're going to be impacting that material there. And that material, that part of the field where a lot more diving and so forth occurs, and a lot more movement occurs in terms of the goalkeeper potential exposure, is going to be different potentially than other parts of the sort of the general field. And so it may be more compacted, it may be more diffuse, it may be more torn up, whatever the case is. Just anecdotally looking at a field, you see that the field, it's usually bare in front of the goalkeeper's spot there on the field. And so I think that is a separate part. So I would echo Linda Sheldon's comments that, you may want to think about the goalkeeper sort of area as a separate area, because you may find something different there.
So thank you. So I want to ask staff, have we answered questions 1 through 3 adequately for you? I know question 4 we haven't really addressed about mercury. Any other questions, Patty? Any remaining issues?
I agree.
Okay, so with regard to mercury, basically, since they didn't find very much in terms of mercury, I think the point is here they'd sort of like to stop measuring it. Debbie?
Have they done it? You guys have done at least one mercury sample per field at this point, right? Okay.
Yes. Yes.
So what does the panel feel about, question 4? Have we done enough to understand the mercury content in crumb rubber used on synthetic turf fields?
Can I ask a question? And I'm not familiar with that literature. People tend to do metals when they do pilot studies or whatever study. Have many of them done mercury before? Do we have much literature data for mercury on fields, and is it considered a problem?
For the recording purpose, sorry. It has been studied before when we do initial literature search. Mm-hmm. Mercury has been looked at in a lot of the study, and it hasn't been popping up as a concern.
Then I would think that if we have data on one piece of data on each field and it has not been raised as a concern, that you could probably drop it.
That's my take, but I wanted the rest of the panels. Dr. Kyle, do you feel differently?
Can we go to the slide number 68? So as it's shown here, it's in nanogram per gram rubber concentration we have been seeing, and most of the data are below the 1. The method detection limit is a 100 part per trillion.
Yeah, I was reasonably convinced by this plot, but I'm relatively naive about this as well. Tom, I'll pick on you. What do you think?
What I'm struggling with is whether, in the context of impact, whether this is going to be, whether this is going to be something we worry about for the population, right? Is this going to be an important source of mercury, and do we have enough evidence to say, look, it's not what we're really going to be dwelling on is the dominant contributor to health impacts, and if there's a way to sort of come to that point, with the preliminary data we have, it'd be nice to discount it because it really opens up a lot of difficulty.
Well, so the total number, the total amounts of mercury are in the microgram per kilogram range.
It's a nanogram per kilogram. Nanogram per gram, yeah.
Microgram per kilogram,
yes.
Which is an environmentally relevant range. And so it's the ASTM method that's below detect. So it somewhat turns on how good that method really is. And I'm dubious because there's been a lot of issues about when my mercury really is or isn't bioavailable and what turns it from one state to the other. And, for a long time we thought mercury wasn't bioavailable or it didn't get methylated, et cetera, and then it turns out it does in settings where we thought it didn't. Now, I don't know enough about your method to say that it's good enough to say this doesn't matter. So that's where I look at this and I say, well, maybe we need to just look at this a little bit more carefully. Because I don't know why you would exclude mercury just based on these data vis-a-vis the numbers actually in the turf material. Or is that what you're saying you would do, the blue numbers?
What we are trying to propose here is, to show here is the level. We are not excluding mercury in our discussion or exposure evaluation or risk evaluation. These numbers will be here for our report and will be assessed. What we are saying that, do we have enough data now, knowing that it's a lower concern, and the amount of effort to go in for chemical with a very low level is being fluctuated in the background. Are we getting meaningful data from it to get more data? That was the focus we have.
And the more data is analyzing more of the samples that you have?
Correct.
Can I ask a question about your method? I mean, I know that to do mercury, you have to use clean rooms and all kinds of clean techniques. And how much contamination do you see with your mercury samples? Are you really close to the level that, your clean handling, some of it could be really just handling contamination? How certain are you of that data? And I'm not trying to insult you as an analytical chemist. I'm just trying to...
No, it's an excellent question because we know metal analysis, ICP-MS has gotten so good, to the PPT levels that it has to be run in a very clean environment.
Right.
People that run ICP-MS laboratories are extremely careful with contamination, and that is a real issue. So we looked at the blanks. We have blanks for each of the The analysis of all these 70 plus samples has been done in 5 different batches, so it wasn't all done together. And we looked at the blanks for each of those batches, and those differ. So we can see that from, say, 1 month to the other, the same laboratory and everything else gives you maybe one day gives you 20 ppts, and the other month gives you 70 ppts. So there is some fluctuation on the blank. These are really low levels for a blank, but that's what it is. And then the samples that are analyzed side by side with those blanks are about the same level for the most part, for the ASTM method.
Okay, so oftentimes at low levels, and it's really very rigorous, is that we will take the standard deviation in the blank and, take the average plus 3 times the standard deviation to say this is what the method detection limit is, because that's when you are 95% sure, or whatever it is, that you are actually measuring what is in the sample and not in the blank. Is this detection limit more an instrumental detection limit, or is this based on the contamination in the background? Because if it is, you may not really be detecting any mercury at all.
Yeah, we went back and forth on this in terms of which criterion to use. And this one that is shown there is based on the.
I think what I heard was is a 10 ppt is the instrument detection limit. So the instrument itself, ICP-MS, is 10 ppt trillion, and we have a tenfold dilution in our sample. That bring up the instrument method to become a 100 ppt detection limit. This is what we draw here. It wasn't the blank.
Okay.
It wasn't the standard deviation plus the blank.
So you might look at that and really see if any of those are really would meet that more rigorous detection limit. Because I think there's always the danger that if you start reporting sort of just random contamination, mercury can, send up a lot of signals. So you might also consider that.
Absolutely. Thanks very much. And we agree that, we looked at a few criteria, and definitely, for example, for the EPA data, with a more strict criteria, you could have 20-30% of the lower level data fall under the limit of detection. Definitely that would be the case. Good.
Mr. Apel?
Just in terms of looking and trying to make decisions about your data for these 10 or 12 samplers that are detectable, have you looked to see if they associate with anything else that in your data set? I mean, are those characteristic of some other that could be used as a marker for these?
You mean correlation with other analytes? No, we haven't done that analysis yet.
This is a 70 sample we have plot. So they cover all the 35 field, and some of them cover the whole field, the 10 sample per field. So is what we presented at the beginning, the 19% of the sample, it has multiple field, all the field actually, and different level of completeness per field. Each data point here represents a sample, so we have 70-something samples.
Dr. Bennett?
There are 2 points that were above 20 on the ASTM method. I don't know if those are individual fields. I mean, maybe if those were one sample from each of those fields, those 2 fields would maybe the ones to dig in on and see more spots on that field, because maybe that was random contamination, or maybe you do truly have a couple fields that are high.
Yeah, that's a good point, and we did think along those lines in reviewing this data for this plot. Exactly.
Any other panel comments? Patty, you feel comfortable with the responses you got?
Definitely.
Okay. Maybe it's time for lunch break. I've been...
but we can stop now.
So we could either stop now, or the next presentation is on the VOCs and aldehydes. And I'll have a preference? Plow forward or take a break? Pardon? Okay, I think that's a good point. So it'll be quick if we're before lunch. So let's go on to the next presentation on aldehydes and VOCs.
All right, I'll try to be quick then. So I'm presenting a preliminary analysis of volatile organic compounds, which I'll refer to as VOCs, at the synthetic turf fields. And I'd like to give a big thank you to our student assistants, Sarah and Jen. They worked very hard for us last year, and in a 6-month period, we processed about 800 volatile chemical samples. And so that created a very large database, and I'm going to be presenting just a small percentage of that data today. Okay. So a quick overview, and some of these you've seen with Woody and the particle sampling. Our chemical samples were deployed in much the same manner, so I'm going to quickly go over the sampling strategy, brief look at our analysis methods, and I'll go right to the results on VOCs and some formaldehyde results. So again, here's the same figure showing our goal for the sampling event, the goal box. So we measured in 4 places on the field. Positions 1 and 3 represented our spatial or horizontal measurements across the field. Position or cart 4 was off field, and cart 2 was directly behind the field. So cart 2 was our unique sampling position. We called it the sampling tower, and this allowed us to get the vertical variability on the field. We sampled at 4 different levels, with level 4 representing an adult breathing zone at about 65 inches. Levels 3 and 2 representing perhaps a teen or a child's breathing zone, and level 1 being closest to the field at 4 inches. Here is, again, our activity timeline for what was going on in the field, and represents the temporal resolution in our VOC and aldehyde sampling. So the gray arrow shows the duration of the sampling event, which lasted about 5 hours. The red arrow is showing the activity period, which lasted for 3 hours, from periods between hours 2, 3, and 4. So VOC sampling took place every hour. We used a specially designed sampling box, which is shown in the upper left corner. And here you can see the thermal desorption tubes, which are deployed in the ports of the box. The sampling box contained pumps, valves, and electronics to automatically sample in sequential order from VOC number 1 to VOC number 5 at the last hour. And you can see labeled on there the blank tube, which was in position 6. This allowed us to include a field blank with every sampling box. So 5 VOC samples were collected in this manner at the 3 different locations, carts 1 and 3, which were next to the goal box, and cart 4 off-field. These boxes were also synchronized to begin the sampling event simultaneously at these 3 locations. So sampling on the tower positioned happened only during the final hour of activity, as indicated in VOC number 4. So all 4 levels of the tower were collected simultaneously just during the 4th hour. Finally, the aldehyde sample consisted of 1 3-hour integrated sample taken during the active period. So these were taken in duplicate at positions 1 and 3 on either side of the goal box. So the volatile organic compounds, which were collected on the thermal desorption tubes, were analyzed by thermal desorption, gas chromatography, mass spectroscopy, and that's EPA method TO17. Our volatile aldehyde species were collected on a commercially available cartridge, and these were protected with an ozone scrubber since aldehydes are sensitive to ozone. And we used EPA method 8315A. So sample integrity was protected by a variety of quality control steps, including travel and field blanks, barcoded sample IDs, sample tracking database, and chain of custody forms included with each package. So next I'll show some results on the VOCs. I'm going to take a look at the vertical and temporal distribution of the VOCs and then some formaldehyde results. Here's a first data slide. So to look at the spatial variability found on a typical field, I'm showing a one-to-one plot showing the relationship between on-field and off-field samples. This graph uses the VOC sample collected during hour 4, the last hour of activity. And I'm showing results from cart 1 and cart 3, just labeled here position 1 and 3. So position 1 is the blue dots, position 3 is the open circles. So these are plotted on the y-axis and compared to the off-field cart on the x-axis. So each circle here represents a specific VOC. In a typical VOC sample, we can identify about 100 VOCs, and this is using a NIST database, which matches the mass spectral data that we've collected. Air concentrations are normalized, so we're just looking at relative differences among the VOCs collected in these samples. So we can identify 3 categories of compounds. First category is on the one-to-one line, and these represents chemicals that were present in equal amounts, found both on-field and off-field. Second category, you'll see a group of chemicals that lie only on the y-axis. These are a subset of chemicals that were found only in the on-field samples in both positions, cart 1 and 3. And finally, the last category, there will be a subset of chemicals found only in off-field. Okay, so from the on-field chemicals, we've identified subset. I'm gonna focus on only 2 of them that we've identified. One is benzothiazole, and the other is methyl isobutyl ketone. Their structures are shown here on the right. Both of these chemicals are also known markers of tires. So this slide is looking at the vertical distribution for these 2 chemicals. And what I'm showing here is an average of 5 fields, and I've normalized the relative response for these. So we're just looking at the changes among the 4 levels that were collected on our sampling tower. And you can see at level 1, which was the level closest to the field, we have our highest amounts, and you can see the decreasing concentration as we move away from the field. So now the temporal distribution of these 2 chemicals, benzothiazole and methyl isobutyl ketone, is shown here. And again, this is looking at an average of 5 fields and reporting a normalized response. So we're just looking at changes that occur during the sampling event. You can see on the x-axis is the time from the first hour through the 5th hour of the sampling event, the activity occurring between hours 2, 3, and 4. Methyl isobutyl ketone is in orange, and you can see it remains relatively stable throughout this sampling event, while there are changes occurring for the benzothiazole. And now some formaldehyde results. This is showing a distribution among 30 fields. So we took 2 samples at each field, and we averaged those. And I'm just showing here the distribution for all fields through the concentration. And none of our samples exceeded 6 parts per billion. So we measured a range from 0.4 parts per billion to, I believe the highest was 5.3 parts per billion. And you can see the incidence of the concentration ranges here. But overall, it was quite low. that is all I have today, and there's a couple discussion questions.
Okay, so John has left, and I'm taking over for John. How about we go left to right? And so, Sandy, do you have some comments here?
So I haven't quite had enough time to finish reading the discussion questions,
Oh,
but I think they're a
okay.
bit outside of my expertise area, so I'll make one other comment.
Okay.
Just in terms of statistical presentation of the results, I think it'd be nice, especially for these results, like on slides 84 through 86, when there's sort of averages of a number of fields, if we could maybe see the variability between fields by displaying the actual data points or some sort of error bars, that might be helpful for helping us understand the trends.
If you could put it to the slide 83. Yeah, and you can put the circles back. Or, I'm sorry, 82.
Put the circles back
Wait,
on it.
yeah, this one with the circles.
So
There we go. Thank
this
you.
field, this
got a different
presentation
number,
was
but-
not an average, so this is just one field.
No, I understand.
okay.
So what I'm thinking, and I'm like kind of dangerous when I talk about non-target because I know not very much, but I know in some of the analysis work that we've done with dust, we've looked for consistency of chemicals with certain patterns. And so I'm wondering if really the answer to number one is if you plot, but these are ones you've already identified, or are these the ones you have a peak location?
It's both. They're matching retention times, and they've been identified.
And then do you have some other where you just have the retention times, but you haven't identified them?
Those do exist. They are not on this plot. And those
So
in
what-
general are very low peaks with poor signal to noise. They're going to be hard to get a NIST match with
So what I thought
strong
might make
confidence.
sense on those is if you have some of those where you have peak locations where at the on field but not the off field, and you have a consistent, albeit not that well defined, at a consistent retention time, and looking to see, like, if I'm seeing that retention time as one that's in that sort of orange circle on over half my fields, then maybe it's worth the time to dig on those. But if it's just a one-time thing, it doesn't make any sense to me, you know? But if you're seeing that retention time on field consistently, that could be something of interest. And because, you know, if it's showing up commonly, would be my thought on number one.
I agree. I think that would be a good approach to look for a signature of on-field
Yeah, because
characterization.
then maybe it's some chemical you do care about, even though you haven't been able to figure out what it is at this point. So that's my thought on number one. And then my thought on number two is, again, those ones that were in that orange vertical box, looking to see how often those same chemicals were popping up on various fields. Because if you're consistently getting in that vertical orange box, then that seems to me that that would definitely be a chrome rubber marker.
Okay. Ed?
So if you're implicitly assuming that the benzothiazole is you're effectively a marker for the chrome rubber for tires, have you looked at this? I mean, there's only 5 fields, so it's hard for me to sort of interpret this because I don't understand the temperature paradigm here or the wind direction, wind speed temp, but it looks sort of like over the course of the 5 hours, basically, are we saying that it's getting hotter in the afternoon and the wind's coming up?
Yes, exactly. I think that's very important that we need to start overlaying all these parts that we've collected, especially temperature and wind.
I mean, I think it's hard for me to sort of understand it without that interpretation.
Amy?
I second the comment about considering frequency of occurrence as maybe the most important thing when you decide how much effort to put into tracking these down. That makes perfect sense to me. A question I have is, what do you mean by crumb rubber marker? I mean, why is that? What concept is that? Because we're trying to find pollutants that come off crumb rubber. So we know we have, so I'm just not sure, is that something different than that, or is it the same thing?
It's the same thing. And what we've done in-house, we have the crumb rubber samples from the manufacturer. We can put in an emission chamber and we can see what chemicals do come off of it, so we can confirm what we see on the field and say this is our signature.
So you're just trying to distinguish those from other background airplanes?
Exactly, from the environment.
Yeah, okay. I just wanted to clarify that.
Tom?
So one thought, these are volatile chemicals coming from crumb rubber, and I know there wasn't a lot of work on aging, but you must have some sense of the age of the different fields. And if you could look at a trend line, in a way, I think this is a way to deal with number 2, things that are showing, they should show, or you probably will see a decrease in time. I'm guessing that the volatile inventory is going to decrease in time as the field ages. And I mean, that might be a way to confirm that these are crumb rubber if they're showing this, the things that show that trend with time, particularly when they show the on-field trend in falling off with time. Just a thought. I mean, but it would be interesting to do a little bit of the trend line for the age of the field, because for volatiles, I would expect, for semi-volatiles, probably not, that'd be difficult, but for volatiles, they should start depleting their inventory within a year or so, right?
Yeah, I agree.
Okay. Do you have a comment? You go first.
The other thing, there was a recent ES&T paper that talks about some semi-volatile markers of tires. And if you guys send me a note, I can send that back to you, because there was somebody that was just looking at some of those markers, and they were using a non-target method of things that weren't commonly studied. So that might be another useful resource.
Okay, I have a few comments here. One is, I think it would be interesting to, and maybe you've already done it, is just look at the total ion chromatogram plot, both on-field and off-field. That will tell you, it's sort of like indoor-outdoor air, even though the chemical concentrations may not be different, you see a whole lot more stuff indoors. And so even that would tell you whether or not you need to spend a lot more time worrying about the tire crumb markers. And so I would try doing that on the indoor outdoors. I really would like to see some, pattern recognition. I used to do a lot of work with PCBs, and what they do with PCBs is you look at the pattern recognition and you say, oh yeah, that's a PCB, and this is the way I'm going to quantify it. And if you can develop some, I can't remember how I did it, this was many years ago. But again, I think that since you have the tire crumb from the manufacturers, you should be able to get some kind of pattern recognition, either on the total plot or looking at specific ions in the plot, and see if you can carry it that way. I think this is something the statistician could have great fun with, or that's what I keep telling myself. I used to tell statisticians, but I think that might be one of the ways to go. And then for those things that tend to look like they are a real issue, then you might try to identify them. Yes, I mean, once you've got all these little peaks in the middle of nowhere, it's almost impossible. And I think that you don't want to be identifying chemicals where you've got a great deal of uncertainty about what that chemical is. And so, if you think it's a chemical of concern, if you think you've got a pretty good idea about it, then I think you've got to get standards and you've got to run it, and then you have to do some matching. But again, you are addressing a public concern, and so you do need to be careful. You need to be thorough, but you also need to be careful. Okay. So, any other comments? Did you read yours? Not your field. Okay. Any other comments by the
Just one. So did I misunderstand you? You have the crumb rubber samples from each field, and you've run those in the lab at different temperatures, or?
We haven't done that. We did some initial studies with crumb rubber that was uninstalled, new from the manufacturer, and we have emission chambers. So
for whatever data you have for the data set of the crumb rubber from the manufacturer, for a given field, have you looked to see what the characteristics of that data is from the sample and from the field?
Not completely. There's definitely more to do, but as far as identifying, some of the top chemicals like the benzothiazole and the methyl isobutylketone, there's been some preliminary work with that.
Thank you.
So Lauren tells me that we can come back at 10 after, or we should be back at 10 after. I think that's what she meant to say.
105.
Right, 105, and we'll convene at 1:10. Thank you.